So thank you. Thank you for the invitation to this great conference. I'm going to talk about, I have a bit too many slides. I hope you will survive. The finest weapon I will be using is Taylor expansion to second order. So, but I'll try to be as brief as possible. This is joint work with Gibbs-Boltzmann, who is now emeritus in Frankfurt. Mario Schmidt is a postdoc in Basel. Adrian Scherzer is doing his PhD with me in Frankfurt. I added this sentence strongly influenced by Tim Plewka. He's a theoretical physicist. He's retired. And Arnoud van Enter, they have tremendously helped me shape a certain point of view. It's about spin glasses. But in fact, I will start at the risk of boring you with the Curie-Weiss model, because this will help me set the staging for the Parisi solution, in particular the puzzles that it raises, and then I will go back to the Curie-Weiss model with a apparently new, I'm not sure, approach, which will allow. I will then work out the consequence for the SK model and concerning the puzzles raised by some puzzles raised by the Parisi solution. I'm not sure I will have time to talk about this Towles-Anderson and Palmer approach. It will be the only part of my talk which has something to do with random geometries, but it's okay. Given the time, we'll see how far we go. So the Curie-Weiss model is a prototype for a mean field model. One is given a configuration space of Ising spins. So it should model a chain of atoms with spins plus or minus one. The size of the system is this number n, which will then typically go to infinity. The average of a configuration is given by this two-body interaction, the sum over all possible couples. It should represent the interaction among the atoms. Okay, it's a mean field model, and every pair of couple is appearing, and everybody interacts on the same footing. The partition function is the sum over all possible configuration of the Boltzmann weights. I'm not sure. I'm using. I might be confusing physicists. The minus signs. We have slightly different notation in mathematics, but. I hope you will survive. I mean, you survive Anderson localization, you will survive this minus sign. So the free energy is then, okay, is the logarithm of the partition function normalized by the size of the system. And the typical question we ask as the first question is, so what about the infinite volume limit if the chain of atoms goes, you have infinity many atoms? And I would like to recall, and this is something which is, of course, well known. It's this Gibbs-Boltzmann framework, which is somehow the fundamental principle of statistical mechanics, which relates the free energy, so the logarithm of the partition function, with it's a representation of the free energy in terms of variational principle. So it's given by the maximum overall probability measure on the configuration space. Of the internal energy, so rho is any given probability measure on the configuration space, the internal energy minus the entropy, the relative entropy, which is of course okay, the integral of the log of the Radon-Nikodym derivative. Now, in my setting, this variational principle is concave in rho for finite volumes. And this is absolutely a key aspect. It encodes the stability, at least in finite volumes of the system. And there is a unique maximum, which is given by the Gibbs measure. So this is one important thing to remember is that this variational principle in the form of a maximum and a concavity principle. Now, let me recall, as far as I know, there are essentially two ways to solve the Curie-Weiss. One is by Haber-Stotanovich. The one which is perhaps a bit more constructive and is a bit more insightful is so by simple counting, essentially. It's based on realizing that the Hamiltonian can be written as the square of the magnetization, which I'll denote sigma bar. Okay, then instead of summing over the sigmas, the configuration, I can regroup this integral, this sum, according to the possible magnetization. So I will fix it to equal to m, and then so the Hamiltonian is just a function of this magnetization. And okay, of course, we can simply, it's a simple problem of combinatorics, counting how many configurations have this specified magnetization. It's given by this function Im, so it's the coin tossing function. It's a problem of large deviation and Stirling approximation. Anyway, it's once we are so far, and so we are done essentially by Laplace principle. The logarithm of the sum is concentrated of the maximum of this function. And so taking the limiting, so this indeed everything can be made rigorous, of course, and so we have that the free energy converges to the maximum of this object. Now, just to remind ourselves, the finite volume free energy was defined essentially as the maximum of an internal energy minus the entropy, and in fact, we can replace this with the infinite volume limit. It's a maximum of the internal energy minus the entropy. And furthermore, the other parameter is a physical quantity, is the magnetization, something you can easily measure in a lab. It's this m. This to say that this solution perfectly fits into the Gibbs-Boltzmann framework. It's neat and clear. But what about as soon as we introduce disorder, things get a bit more puzzling. So the prototype of disordered system, mean-field systems, is definitely the SK model, which is the setting is essentially the same as in the Curie-Weiss model. We have a configuration space of Ising spins, but we then introduce disorder to modulate the interaction, and this was motivated studies on experimental studies on some special alloys. As an approximation, at least, and the celebrated SK Hamiltonian is then the sum of all possible pairings is a two-body interaction, but these two-body interactions are then modulated by this disorder. These Gij are assumed to be Gaussian. It's not really important by universality phenomena. They're independent standard Gaussians, and something I want to really emphasize is. In my point of view, is here's the devil is creeping in with this normalization. Of course, this is the right normalization because of cancellations, but this is the beginning of lots of sorrow. The partition function is defined just as the quench partition function. So this is still a random variable, this h and sigma. So I might allow some external fields, some magnetic field. The partition function is then okay, the trace of the Boltzmann weights. And the quench-free energy would be just the same as in the Curie-Weiss model, is the logarithm of the partition function. It is known that the quench-free energy is in fact self-averaging, so in the limit n to infinity, it doesn't depend on the disorder. And in fact, the limit coincides if I integrate the disorder out, which I will do in this case. So I call it quench-free energy by integrate out the disorder, but of course outside of the logarithm. Now, what about the Parisi solution and then the puzzles it raises? The Parisi, some aspects, it's a huge picture, but some aspects I'd like to recall of the Parisi picture is, for instance, this one. So Parisi says, consider a non-decreasing function mapping the unit interval on itself. They can be a step function or continuous functions. And then there is a nonlinear partial differential equation, some sort of it equation plus a nonlinear term, which depends on your choice of non-decreasing function. You're supposed to solve this function. Q should be thought as time, and y is in one dimension. It's a spatial variable. We should solve this partial differential equation with some specified boundary condition, and then evaluate it at time 0, and this spatial variable should be replaced by the external field in case you have it. Subtract something which still depends on the choice of a function you have made, and then compute the minimum of this variation of this expression over all possible non-decreasing functions. And that was the famous conjecture by Parisi that this is the free energy. In fact, it turns out in infinite volume limit, this has been proved rigorously by Guerra and Talleyrand first, and then Panchenko, that the free energy of the SK model converges in the infinite volume limit, indeed, to what Parisi had predicted based on his mesmerizing replica symmetry breaking computation. And here it all begins somehow as far as this talk is concerned. So here's the first puzzle. And so you see, it's a minimum over these non-decreasing functions. And in fact, in Boltzmann-Gibbs principle, or we worked it out in the Curie-Weiss model, the free energy was the maximum of internal energy minus the entropy. Now you could say, so why is this a minimum now? Okay, the question why is rather related to the fact. And so to another question is, what is this object? Now, in order to not to be scared by the complexity, there is a partial differential equation standing behind this object, but it's not. I think that that complexity is not really the point. And in fact, for small beta, we know that this object takes a much simpler form, which is given by this expression. The free energy for small beta is given by the minimum over. It's now a one-dimensional principle. This was an infinite-dimensional principle of this this quantity here. Wherever you see a G in my talk, it's going to be a standard Gaussian, and E is the integration with respect to this type of disorder. But now, if you look at this this object. One question is what is it? And the question, what is it? I think it's a clear question. Is for instance, this has some flavor of an entropy, but it has a wrong sign. It should be a minus sign in this case. You can move further and say, okay, so is this perhaps an internal energy? But in fact, if you look closer, there is something puzzling here, and so which is this beta squared divided by 4. If there is no h, and so this object drops out, and this minimum is given by beta squared divided by 4, and this is 1. But this beta squared divided by 4 is essentially the inverse of the temperature squared. Now, what kind of physical object is this thing? So it's what kind of unit? What's the meaning of this term? Now, another question is, so now we're minimizing with respect to this number between 0 and 1, and you can ask, it's okay, so, what is this? This obviously has the nature of an order parameter, it drives the whole system, but you may ask, what is it? Now, there is one interpretation of the optimal order parameter, I'm not so sure it's a good one, and it goes as follows. You take the variational principle of Parisi, and you find the minimizer. In fact, it's, this variational principle has a unique minimizer. It's been proven, I think, a couple of years ago. So you can you can define it uniquely, the minimizer. Now you can consider the overlap of two configurations, sigma and tau. And so which is sigma and tau are two vectors of plus and minus 1, and the overlap is the scalar product of these two vectors. Turns out the scalar product is also related to the covariance of the Gaussian field. It's a square of the covariance. And you consider the Gibbs measure over a replicated space. I take I duplicate the space and I endow it so with a product Gibbs measure with the same disorder. And then the corollary is that the optimal order parameter, this object here, is the law of the overlap. So the scalar product of two randomly chosen under the Gibbs measure configurations. The distribution of this random variable converges to this optimal order parameter. You could say this, okay, then we have an interpretation. I'm not so sure, because this overlap is hardly a physical quantity. If you think about it, and so how it was defined, I have my two pieces of copper magnesium, and the overlap of this which is appearing here as the order parameter of the theory, is the scalar product of these two chunks of metal. So I'm not so sure about the meaning of this, but this is a fact. I mean, this is true. This is mathematically even proved. But it's about interpreting this. And so, and these are only some of the I'm not entering the more complicated and deep aspects of the Parisi theory, but these are certainly some of these of the puzzles they seem, I mean, to me, they seem to touch upon fundamental issues, but I'm not aware of, at least in mathematics, of papers addressing these, although we have a confirmation of some of the prediction by Parisi, rigorous confirmations. And to me, there's a sentence which does strike a chord. And it was formulated by Nicola at a meeting in 2003. And he said that the goal is to shed light on the Parisi theory through an analysis which is both rigorous and based on physically recognizable principle. So that was Michael Eisenman in Oberwolfach, almost 16 years ago. Well, I think the goal still is to an analysis of the Parisi theory through, which is rigorous. Okay, we're mathematicians, but which is also based on something which we can recognize. And let me emphasize that this goes at least when mathematics is concerned, it goes beyond the quest for understanding, because at least mathematically, well, definitely mathematically, we have a current machinery which comes to a complete stall for a huge class of spin glasses, like the perceptron or the optical or models, Hamiltonians, which appear in combinatorial optimization. On the other hand, it's amazing. Parisi approach is universal, it's slick, it's fast, and we are definitely missing something about spin glass, because it cannot be that the replica computation work is virtually for any model, but when it comes to mathematics, it will come very easily to a complete stall, so there's something which definitely has to be understood out there. Now, if you go back to the goal is formulated by Michael Eisenman, you may say, okay, what's a physically recognizable principle? Now, I'm not so sure I have an answer to that, but at least for this talk, the goal would be to recast the Parisi theory into a framework abiding to the principle of thermodynamics and classical statistical mechanics, because that's where they were defined. So somehow the goal is to bring these spin glasses back home, which is the reason of the title, From Parisi to Boltzmann, which is pictorially should look like this. This is the goal. So to bring these two gentlemen together. Now, I will now go back to the Curie-Weiss model. And I will discuss something, another approach, which is based on the introduction of a Gibbs potential and high temperature expansions. So the idea is the following. I'm looking at the Hamiltonian of the Curie-Weiss model is some of these two body interactions. Now I want to single out the spins. Of course, we can do it in this simple way. Because this, okay, I call them effective magnetic fields. And so what these are doing, well, it's essentially what the spin sigma I feels because of the presence of the other. It's a magnetic field which is induced by the presence of the other spins and the interaction. Now, here's the first realization. Okay, it's a mean field model. So the Gibbs measure, in fact, should be approximately a product measure. This is definitely a very natural thing. And this is because there is no concept of distance. So if the spins are not independent, then they are correlated. But then we should say, how are they correlated? But the correlation cannot decay. So there is not much room for freedom. The Gibbs measure must split into a convex combination of ergodic pure states. And so, from a mathematical point of view, we would rather think of definity and exchangeability properties, but they all come to the same conclusion. The Gibbs measure should be approximately a product measure and remain so in the infinite volume limit. Now, ergodic pure states is, I think, it's the physicist way of putting this feature. It's a product measure. So this somehow means that this effective magnetic field should be effectively be replaced by something which is not depending on the sigmas, because this is the only possibility to have a product Gibbs measure. namely a Hamiltonian of non-interacting sigmas. And this, I will use it as an answer for the free energy, to compute the free energy, or at least to get a handle on it. And the answer is based, in the answer it goes as follows: the free energy should concentrate on sigmas such that, okay, we have these effective fields. It's a sum of n terms divided by 1 over n. Well, it's very natural to believe that this concentrate around its, its mean, the Gibbs measure. Okay, I put here with a cavity in I to avoid the rebouncing effects. But once we have that, it's okay. It's by linearity. We can write it out. And so it's a sum of the mean magnetizations, which I call mj. And then again, so this is a sum of n minus 1 terms divided by 1 over n. It should converge in the limit to something, which is this, which I call mi. And of course, so by exchangeability, everything is symmetric. And there is no reason to believe that these mi's are all different. And so I'm assuming that these effective fields converge to one and only number. And this is essentially what I'm saying, is that the answers I would like to make is, for these effective fields, is a law of large numbers phenomenon. Now, how to use this? It's okay. I'm shortening to Leiden notation. So the Hamiltonian times the energy. These considerations, they suggest, okay, maybe we can work with the following answers. So I'm introducing this function g alpha phi is the log of the partition function, but a slightly modified Hamiltonian. So this is the original Hamiltonian multiplied by alpha, and then I add these fields which are justified by the answers of a law of large numbers. And so there's this key correspondence is this phi should morally correspond to the mean of the effective fields under the Gibbs measure. And the alpha, I will use it as an expansion parameter. It will be a number between 0 and 1. Now, as it turns out, okay, this map, now it's a map on phi, and alpha will be chosen later. This map, of course, is convex by Jensen's inequality. So the of a convex function is well defined. So I will consider the Legendre transformation, which is this object. This is maximum overall possible phi m minus the function. Now this is it's important. This is the maximum because it's a convex functional. Now, of course, so you recognize this. I'm introducing a Gibbs potential, a Helmholtz free energy. Now the idea is. Okay, so if you wonder what are the phi duals, well, you solve this variational principle with respect to take the derivative with respect to phi, and then you will see that the m are essentially, they correspond to the mean magnetization under the Gibbs measure with this Hamiltonian, modified Hamiltonian, which is indeed what we're expecting. So because we're talking about the mean magnetization as hiding behind ansatz. And finally, so okay, it's the map is convex. I'm working with Legendre transformation. Legendre transformation in this case is an involution. So if I do it twice, I get back the original function g alpha. But now if I evaluate it in alpha equal to 1, and I set this phi equal to 0, you see this drops out, and so alpha equal to 1, I get the free energy back, which is the one I want to compute. Okay, so I'm just reformulating this sentence. Now the idea is, okay, this high temperature expansion. So the idea would Taylor expand around alpha equal to 0, and alpha equal to 0 is a smart choice because with alpha equal to 0, this drops out, and what remains is a non-interacting Hamiltonian. So there's a good chance that we can do the computations. So this is a Taylor expansion. Now, if you do this computation, there are computations, elementary computation. So you will see that the first term here is something you immediately recognize is the coin tossing rate function. The first order term is the internal energy, which we have seen in the other approach. And then there is something absolutely stunning to me is that the second order already drops down to something which is irrelevant in the thermodynamical limit. And you can compute, of course, the third and fourth, and then they are all of irrelevant size. Okay, this is to me stunning because I don't understand. But if you assume that this is so the starting from the second order onward, there is no essential contribution. well, then what remains is a very simple expression, and the expression is something we recognize. There is there is definitely a problem here, and so is that this can only hold I'm dropping all this contribution, but this can only hold if this expansion is absolutely convergent up to alpha equal to 1, because alpha equal to 1 is the one I need, because it's the one I need to recover the free energy. Now I'll come back to this delicate point later, but definitely a necessary condition is, we started with a convex function. We need to have a convex function or a concave function, then we need it back. So this is essentially a necessary condition for the expansion to converge. Okay, but let's use this as a restriction, and then of course, so we can solve this simple one-dimensional problem. It did coincide with the solution of the Curie-Weiss, which we have obtained via the classical approach. So this is news. I'm not claiming I can do this rigorously. I'll come back to this later. But in any case, so the procedure seems to be stable and lead to the correct solution. Now, let me emphasize a couple of things. So first of all, these are high temperature expansion, but you see, okay, the Curie-Weiss model without external field, like the one I'm using here, it undergoes a phase transition. There is a high temperature and a low temperature regime, but these high temperature expansions, alpha is small, is at most 1, they seemingly recover the correct free energy for any beta. Now, this could be also in the low temperature. This could be surprising. Because the outcome is correct also in low temperature, but in fact it cannot be surprising because this feature is in line with the mean field character of the model. Again, there is no distance, the correlation cannot decay, the Gibbs measure splits into can only split into a convex combination of product measures. But now in this model, there are two things. So the product measure property and the high temperature property are just the same. It's two sides of the same coin. So it cannot be surprising that this approach with high temperature expansions works even in low temperature. What? No, beta less than 1. So this beta, the 1 over the temperature, this alpha is essentially 1 over the temperature. It's on the same scaling. So and everything works for small alpha from 0 to 1. You would say that okay, this can allows you to recover the result in the high temperature phase of the Curie-Weiss, but not in the low temperature phase, which would be in this case for beta larger than 1. High temperature expansion do not work for using model for low temperature, but here it works, and I think this is the reason. It's mean field character. It's virtually, yeah. I'm emphasizing this because it's in this order thesis. It's no longer so clear what's going on. But let me work out the consequence for the SK model. I'll redo the same computation, but I'll rewrite, I'll single out the spins, the sigma I, and I want to see these effective fields showing up. And again, it's mean field, so even the quench Gibbs measure should be approximate product measure. This sentence is badly formulated, but let's take it for what it is. But again, so there is a problem. There is this square root of n normalization, and this is a weak normalization. So I definitely cannot expect a law of large numbers to kick in at most weak limits. This would be the central limit theorem normalization. But well, let's make an ansatz which takes this feature into account, and the ansatz is the only possible, what seems to be the only reasonable ansatz, and this will hold only for a small beta, but namely that the free energy concentrate on sigma such that the effective fields, again, so I have in this case, random magnetic fields acting on sigma I, but I claim, I believe that this concentrate around their quenched mean, with a cavity in I, and then it's plain sailing. This is a linear object. I can write it as sum of this sigma j, the mean magnetization, which I call mj. And now if I look at this object, it's a Gaussian, with a variance which is given by the sum of these mj squared. So I assume that this in the limit n to infinity will also converge to some number qi. So what I'm saying here is that the answer is that this effective field are approximate Gaussian random variable with a certain variance. These GIs are ID standard Gaussian by constructing they are independent over the DI. So essentially what I'm saying is that so instead of making the answers of a law of large numbers, it is way more natural here to think of a quintessential limit here to kick in. And then, okay, if we follow the approach we have followed in the Curie-Weiss modeling, so this consideration they suggest to introduce the following function now G alpha q, which is the free energy of an slightly modified Hamiltonian. Now this non-interacting Hamiltonian there is a correspondence in which is this should correspond to the mean, the quench mean of the magnetic field, random magnetic fields acting on sigma I. Here I'm assuming that all the Q's, they could also depend on I, and so but everything is exchangeable again. So there is no reason why this should be, at least you see I'm integrating out the disorder, and this should be all the same. And okay, this is a delicate pointing. So I need to take something which reacts at least to derivatives in the same way as square root of Q. So instead of taking alpha, I will take a square root of alpha. Depending on the model, this is something which is not. There are models where this is not the good way to do this kind of reasoning, but here it turns out that the reasonable choice is to choose a square root dependence. It turns out that this Q map is now for small beta. You can prove it by Taylor expansion in beta. This map is concave in Q. Now instead of okay, I still want to get variational principles, so I will work with Legendre transformation, but now. The map is concave, so the concave Legendre transformation involves a minimum, and this is absolutely crucial. Now, again, by involution, if I apply it twice, and so I get back so the original function, which is the one I want to compute, which is the free energy. But again, this is the minimum of because of concavity and not convexity like we had in the Curie-Weiss. Now the idea is again, so Taylor expand this so in alpha equal to 0, because again, so if alpha is equal to 0, everything can be computed explicitly. Okay, it's again, it's a simple. These are simple computations. You take the derivative and compute the zero order term. You have to solve one variational principle. It's one-dimensional. It takes a certain form, and so the second, the first order term can also be computed. And then there is something again. It's just as stunning as in Curie-Weiss. If you go to the second order, it goes down to something which is in the infinite volume limit irrelevant. And for magic cancellation, so obviously something is going on here. But if you put it all together, you forget, you believe that the second order, third order, and so on are irrelevant, and so you drop them. And so what you're getting is this variational principle, which is the Parisi replica symmetric solution. Now, this allows at least to answer the puzzle I raised. There are many other puzzles in the Parisi world. That first of all, what is the Parisi replica symmetric solution, which is also the one that originally derived by Sherrington-Kirkpatrick? Well, it turns out to be a high temperature expansion of the Gibbs potential, and the Gibbs potential is the one I've introduced before. Now, the other parameter, which is this Q, in fact, it encodes the law of the effective fields. So this is a scalar. It's a scalar number, but that's just by luck, or in fact, it's even bad luck. So because it would have been clearer if right away for the SK model, it wouldn't have been a scalar. But the point is that you see this was capturing the nature of the distribution of the effective fields. I made the answer that it's an effective. The effective fields are in the infinite volume limit Gaussian. So you need two parameters. The mean turns out to be 0, and the variance, which is this Q. But essentially what the Q is doing is just telling me the effective fields are given by the Gaussian distribution. So the Gaussian distribution, it's a distribution. It's a it's not a scalar, but the scalar is enough to identify it. Now, why is it a minimum? Well, because the Gibbs potential is concave in the other parameter. What about the quadratic dependence of the first order correction? Well, if you do the computation, you will see that so this quadratic dependence in the inverse of the temperature corresponds to the first order correction. But if you do the computation, you will see you have to do a Gaussian integration by parts, which increases by 1 the number of derivatives. So the second order this is quadratic. It's a first order, but it's quadratic because of the disorder. If you didn't have disorder, you wouldn't have any quadratic dependence. Now, you may say, what happens? The Parisi theory is of tremendous complexity when beta gets large. And what happens if you have a phase transition, which is definitely detected by the loss of concavity of this object. The divergence of the infinite expansion is a difficult problem. Now, we do have a way, because essentially Parisi, the replica computation by Parisi, they allow you to make the proper guessing. So for the ad hoc Gibbs potential, and we've done it, and then we've checked things. So indeed, we recover through this simple approaching. So consider a Gibbs potential, so expand it to second order, and you get the replica symmetry breaking Parisi solution if you choose the proper Gibbs potential. And there's something which is important. So it's a list of caveats. So I have sketching. So the Parisi solution it emerges from finite volume through high temperature expansion, and it does also for large beta out of a Gibbs potential. I think this explains in physically recognizable terms what the Parisi solution is. Of course, it would be natural. I mean, all I've done is consider the Legendre transformation, take the second Taylor expand. We could try to rigorously implement this derivation, and now, unfortunately, this is, at least to me, it's an enormously challenging issue. It has nothing to do with Parisi, so in fact, I cannot even do it for the Curie-Weiss model. And even this one, I mean, it was kind of a surprise, but it's 2019, and there is something about the Curie-Weiss model which is not obvious. And this is, it cannot be surprising because the approach is to a vast extent, it's model independent. So once you tame the infinite expansions for the Curie-Weiss, you've made some headway, a big headway, but unfortunately, it's nasty stuff. It's it seems to me that there is some expansion. There must be a smart way to perform some Feynman diagrams analysis, but even and there are finally it's something 2 years ago. The Feynman rules for mean field expansion are now known. It's work by Elias and Kuhn, but even that one, it's not obvious how to compute, how to do the asymptotics of the terms. In fact, it's nasty. And so I don't know how to do it. I don't know how to do it for the Curie-Weiss for no matter which model. I think in any case, it seems to indicate there is lots of structure which we are missing. It's probably beautiful stuff, and it's the algebraic structure, because if you see how this magic cancellation happen, that the second order drops down to essentially 0. That's in the third order and the fourth order. And there is something going on. I have no idea what's going on. It's an observation. But the point I'm trying to make is that so my title was from Parisi to Boltzmann, came a bit as a surprise that in fact there is only one way to formulate it. Parisi is Boltzmann. It's something highly it's hiding behind the surface, but in fact there is no need to bring the one to the other. They're already the same person. So except for the B. Yeah. Okay, no, I think it's well, I'm not. You're not tired? Okay. What about there is another approach, so which at first I had thought, so this is a way more natural approach to do things, because Parisi, it's very mysterious. It's the approach by Talus, Anderson, and Palin. I'm no longer sure that this is a natural approach, so for the following reason. So what is the top approach? Again, I shorten the Hamiltonian by I sigma. And I'm explaining, I'm recalling here, so the top approach as advocated, as studied, so by Plewka, in fact. So Thouless, Anderson, Palmer had a slightly different point of view on this issue, but the idea is again to redo the similar steps as we did in the Curie-Weiss model. Remark, it's a P almost sure statement. I'm considering so the Legendre transformation P almost surely, so I'm not integrating out the disorder, which is what Parisi does and what turned out to be easier, at least in this derivation. And I consider this function, which depends on phi, is a function on phi. And now if you can rerun the consideration. This function is convex, just in Curie-Weiss. You go back if you redo the same type of analysis. So you do Legendre twice, and then Taylor expand in alpha. This leads to the celebrated to this object. And this object is easily understood. And so there's a one-to-one mapping so with the Curie-Weiss saying, so this is the internal energy. This is a second order correction, which because of the disordering, so it's not 1 over n. So in this case, you have to go to second ordering. But then if you go to the third order expansion, then you will see that the contribution drops down to something which is seemingly, well, the third order is definitely a smaller order. And this object is known as the top free energy. And that was the claim of Thouless, Anderson, and Palmer, essentially, so that the free energy is given by this variational principle, which looks like a reasonable natural principle. It's fitting in the Boltzmann Gibbs framework. Now, if you so this would be the random geometry. There is a Gaussian random field here, and so and these are just constants. These are just deterministic quantities. But of course, okay, so you're shooting for the maximum. This is the claim of Thouless, Anderson, Palmer. So okay, take the gradient and set it equal to 0. The critical points of this object are then the solution of this set of fixed point equations, which are known as the top equation. And then okay, you could say so it's nice and fine. And so everything seems very natural. But here's an observation. In fact, if we think about what's going on here, and we are introducing n order parameters, one for each and every spin magnetization, because it's natural to expect they will be different. So we're introducing n order parameters to describe a macroscopic quantity such as the free energy. And we know that the free energy is in the limit self-averaging. So this microstructure so should be irrelevant. And the fact that we're introducing n order parameters and the volume goes to infinity means we are introducing infinitely many order parameters. But this is hardly compatible with the principle of statistical mechanics. If this were the case, I mean, Boltzmann taught us so there is macroscopic phenomena emerging which are driven by few parameters. If you need infinitely many parameters, I'm not so sure what's the value of statistical mechanics in this case. And but it's even worse. So because if you look at the order parameters, which are the top solutions, well, they cannot and do not converge because of this normalization. Again, it was the original problem. Is that this normalization is not strong enough to have P almost sure convergence, convergence which is independent of the disordering. So they can converge weakly in distribution. But again, so the free energy is converging almost surely, which is a way stronger statement. So in other words, the top treatment invokes for the thermodynamics infinitely many order parameters which do not even converge. And this is weird. And this is, I think, you can reread this sentence and you will realize. And so, in fact, I think Boltzmann would be puzzled by this. And so if he read something like this, he said, but this is probably not the way to use my theory. But I don't know. I mean, this Thouless, Anderson, Palmer approach is still. I think it has to be amended. And I'm not the only one sharing this idea. Is Plewka, who is one of the major actors in this, also claims that there is something missing in this approach. What it is, I don't know. But I think it's a dangerous. There's lots of problems with this approach. In any case, let me recap. So. I said something about the classical approach of the Curie-Weiss model. I mentioned the puzzles of the Parisi solution, then I've introduced this Gibbs potential and the ansatz of a law of large numbers and the high temperature expansion to solve the Curie-Weiss model. The same ideas apply as long as you take into account the disordered nature. You replace the law of large numbers with the quench central limit theorem. It applies to disordered systems. Okay, and I said something. I think. Okay, if I can summarize it, I think the Thouless-Anderson-Palmer approach misses a fundamental difference between ordered and disordered system, and it's this one. And so one, there are law of large numbers kicking in, and the other one is there are quench central limit theorem. How to overcome this, I don't know. It's a challenging problem. But okay, so the main point is this thing. So the Parisi theory, it's way less mysterious than the top theory, I think. It's the Parisi functional, this complicated, at first sight nonsensical object is a Gibbs variational principle, amended for the disorder.